Hello, this is Deep Thoughts with Deegan, and today I'm going to be talking about radical functions. Now, you'll notice this is not a radical function, but this is a good place to start with this, because what I'm going to claim is that we can turn a radical function into a hyperbola, which is this, and from there use that to simplify and find approximate solutions. So first of all, a hyperbola looks like this. There's a central point, which is called focus, and then it goes like whoop, whoop. And these A and B's are basically just like the distance from, it's like in a circle, they have a radius. It's kind of like that, where A is that distance, and B is like, it's another distance this way. I'm not sure exactly how to describe it, but it looks relatively like that. Now, if you'll notice, from here to here, that does look like a radical function. But there's one more thing that's special about these hyperbolas that's important. And that is that they have what are called slant asymptotes or oblique asymptotes. I like calling them oblique asymptotes because that sounds kind of cool, but I'm going to call them slant asymptotes because that makes it nice. If you look here, we got two. They're actually they're linear. They're not constant on the x or y axis. And the formula to find them in this case is b. It's just b over ax, as long as the focal point is 0, 0. So that's actually not too bad. And then from there, there's not much we can do. But actually, it'll be plus or minus. Forgot about that. It should be plus or minus because it goes in both directions. Now, we're not going to care about what's happening on the bottom. So, hold on. There we go. So I'm actually going to get rid of this because we only care about the radical. And if you'll notice, this is an absolute value. So I can take this, turn it into an absolute value. Using this, I'm going to show you how you can approximate solutions for a system of radical equations and compare them. So now I'm going to show you how we get there. So I'm going to start with a radical equation that's pretty common, or at least a form of radical equation that's quite common. And using this, I'm going to show you what you can do with it, because there's some pretty cool stuff that happens. So it's going to be the square root of some constant a, x squared minus b. Now, if you plug in a negative value to b, it'll become ax squared plus b. Well, plus negative b technically, but you can make it positive. You can make this positive if you have a negative b. Now, I'm going to claim that this function will approach a line that has the slope that's the absolute value of x square root of a. This will be our slant asymptote. And also we can simplify this a little bit, so we have absolute value of x square root of a. And now I'm going to prove this. So we have a function y is equal to that square root of ax squared minus b. First, I'm going to square both sides. Y squared equals ax squared minus b. All right. And then what I'm going to do is I'm going to move the ax squared to the other side. So we're at y squared minus ax squared equals negative b. And what I'm trying to do here is I'm trying to turn it into a hyperbola so I can calculate the asymptotes really quick and easy. Now, the whole proof isn't very quick, but it'll come out with a really nice answer, which was what I was showing before. Now I'm going to multiply by negative 1, or divide, same thing. And what's going to happen there is there's this pretty cool trick where if you take a negative number and multiply it by some difference. Actually, it'll just flip the difference right there. So that's pretty cool, and that's what I'm going to do right here. I'm going to say, there we go, ax squared minus y squared is equal to b. I'm going to divide b from both sides. So we're going to end up with a x squared over b minus y squared over b is equal to 1. Because we want this to be equal to 1, because that's what a hyperbola looks like. Now, we want this to be x squared over something squared minus y squared over something squared. And the way I can do that is, first of all, I'm going to look at this and say, well, that's equal to x squared divided by b over a. If you want to, you can check that. That is true, though. Minus y squared over b equals 1. And we just take the square root of each piece. So we're looking at square root x squared. I'm actually going to move this over here. So we're going to end up with x squared over the square root of b over square root of a squared minus y squared over square root of b squared equals 1 still. Now I can use that formula from before, which is where the vertical asymptote exists, where y is equal to the absolute value of b over a x. And actually, I'm going to make them capital letters just because, so it's not confused with that. This is just coming from these. So big B is equal to square root of B, and big A is equal to square root of B over A. So what I'm going to do is I'm going to plug all that in. So we're looking at the square root of B divided by the square root of B over A. Square root of A, sorry. All right. So, and that's going to be times x, but I want to simplify this. That's going to equal square root of b over 1 times the reciprocal of this, square root of a over square root of b. Those cancel out. That's just the square root of a. And we're already multiplying this by x. So that's actually how we get this. Square root, absolute value of x square root of a, like that. And because square root of a is a constant, you can take that out. So using this, we can approximate where two radicals are very close to intersecting. Especially if you get to really big numbers, it's really hard to approximate, especially when we're talking about integers. Even with this, it was hard to approximate for integers, but I'm going to show you an example where we can. So this is the example I'm going to be working with. I chose it because it works with, its solutions are going to be integers, and that's nice. Now, it's not always going to be that way. In fact, it very rarely is going to, but I just wanted to show an example that works out nicely so you don't have to think about what do these numbers mean. Because sometimes whenever you're working with these, you'll get a practice problem and it's like, I don't know if I did this right, because you'll get some random irrational number that doesn't make any sense. So what we want to look at here is a 9. We're going to start with these two functions, and I want to compare them. See where this green function is greater than the blue function, where the blue function is greater than the green function, maybe where neither of them exist, one of them exists, or when they're equal. So first of all, I'm going to turn this into a form I can actually use. And the problem with these is we kind of have to approximate for them to get the best answers. And to do that, we're going to turn these into absolute values and work from there. Now, if we look at this function right here, x squared plus 6x plus 9, what we want to do is take the square root we want to factor it. And the reason we want to factor it is what you'll see right now, plus 6x plus 9. If you'll notice, this is a perfect square trinomial. And it'll simplify like this. And the reason it's a perfect square trinomial is we got our a term, which is x squared, b term, which is 3 squared, and then in the middle, it's the product of these multiplied by 2. That's just how this works. And it's going to be the square root of that. Now, when you take the square root of some function squared, it's going to equal the absolute value of that function. So what I want to do here is I'm going to cancel these out, and now I'm going to end up with that's just equal to x, the absolute value of x plus 3, which is pretty nice. Now, erasing. So that's equal to x plus 3, absolute value, x plus 3. Now over here, instead of doing all of that really long stuff, I'm going to use that shortcut I was just talking about. Because if you notice, this is in the form ax squared minus 3, which is approximately going to equal in the long run absolute value of x square root of a. And the asymptote, since it's going to approach that in the long run, we're just going to say it's approximately equal to that, which is going to make our lives so much easier. We get this eraser, and a is, oops, that's supposed to be a b. A is equal to 4. The b doesn't really matter. Technically it's 3, but it doesn't matter. So what we're going to end up with here is, let me erase that so it's nice, absolute value of x square root of a. Now, what is the domain of this? Well, the domain of this is going to look something like, let me think about this. Actually, I'm going to do something different. I'm going to keep what we had before and find the domain first. 4x squared minus 3. Right? So to do that, what I want to do is first I want to find the solutions because there's no y transformations, so it's going to be on the x-axis. 4x squared minus 3 is equal to 0. What I can do here is say 4x squared is equal to 3. X squared is equal to 3/4. And then x is equal, well, the absolute value of x is going to equal 3/4, because if you remember, a square root of 3/4. Because remember, when we take the square root of an x squared, it's going to be the absolute value of x. Now, here's the part that trips up a lot of people. When I first learned this, I hated this. What we have to do here is remember that what the absolute value does. What an absolute value does is it takes a positive input and keeps it positive, and it turns a negative input and turns it positive. So there's actually going to be two cases that we have to talk about. What happens if x is greater than or equal to 0? Which means it'll be positive or 0. First of all, I'm going to show you that it's never going to be equal to 0, because look at, if we plug in 0, it's going to say 0 is equal to square root of 3/4, which it's not, which is very important for a future step. So right here, I'm just going to go ahead and say x is not equal to 0. Bam. That is super important. And also, if we plug it in here, it doesn't work. So now what we want to do is we look at our first case, which is positive x is equal to square root of 3/4. That's nice. Also, we can simplify the square root of 3/4 to be the square root of 3 over the square root of 4. And then we end up with square root of 3/2, which looks a little bit nicer. And also, sometimes on like exams and stuff, they'll want you to rationalize the denominator there, which is just doing that. And this is a pretty easy one to do. Now we have our other case, which is where negative x. Whenever you have an absolute value, you want to isolate the absolute value and take the two cases where it's positive and the one where it's negative. So now we're looking at where negative x is equal to the square root of 3/2. I'm going to go ahead and simplify it down to that. Square root of 3/2. So, therefore, x is also going to be equal to negative square root of 3/2. So I have my two solutions. Now, that means the domain is going to have some relation to square root of 3/2 and some relation to negative square root of 3/2. If we think about it, if the function goes inwards, and if it goes inwards, it's going to exist at some point between. As long as there's no as long as there's no asymptotes, holes, jumps, none of that, because this is going to be a continuous function. So what we can do is we can check a value in between. But we already did. Look, we have 0. So we know these absolutely have to go in opposite directions. So it'll look something like that. And what makes sense here? Well, the one that's less is going to have to be this one right here. So this is negative square root of 3 over 2. And the one that's more is square root of 3 over 2 on this side, which means x has to be greater than or equal to this, or less than or equal to this, because they can be equal. Yesterday I spent 2 hours trying to find vertical asymptotes for these, which is the most stupid thing I've ever done. But these will be equal, right? There is nothing here. It looks kind of odd that it goes in like that, but it does. And so now what we're looking at here is this. And I'm going to write these restrictions right here. X exists such that x is greater than or equal to square root of 3 over 2. And then I'm also going to have and x is less than or equal to negative square root of 3 over 2. Right? That's just what this means, right? It just means these conditions are true. Now what I want, before I go to simplifying this fully, or like solving it, I want to simplify that. And what we're going to do here is we're just going to notice we got the square root of ax squared minus b, where a is equal to 4 and b is equal to 3. Now if you remember, the square root of ax squared minus b approaches, so I'm going to say is approximately equal to absolute value of x square root of a. That's not bad, right? So right here, I'm going to use that shortcut. So what we're going to end up with is the absolute value of x, because we just have an x squared, square root of 4. And I'm going to move this around so it looks nicer. Square root of 4 is 2, so that's going to be multiplied by what's left over, which is the square root of x. So here, I can simplify this down to 2 absolute value of x. 2 absolute value of x. Now I'm going to solve this and use a couple of other tricks that make this possible. So now I want to solve for x. And what we're going to do here is we're going to look at this and we're going to divide by the absolute value of x. So we got absolute value of x plus 3 over absolute value of x is equal to 2. We can transform this into the absolute value of x plus 3 over x. This does not always work, but we know it does work because, one, it can't be undefined, but also x cannot equal 0. And we know that because 0 is not included in the solutions. We have a restriction on the domain right here that cannot be equal to 0. So we know we can do this because if you think about it, you plug in 0 to x, you end up with 3 over 0, which is a big no-no. So now we have absolute value of x plus 3 over x is equal to 2. I'm going to simplify that down to 1 plus 3 over x is equal to 2, absolute value. Now we have to do what we did before and look at both cases. So we're going to look at the positive case first. 1 over 3x is equal to 2. I'm going to subtract 1 from both sides, so we're going to have 3 over x is equal to 1. And you can multiply out, or you can just see it should be 3, but 3 should be equal to x. That's one solution. And remember, when we're done, we do have to check the solutions. For our second case, we're looking at negative 1. Nope. Negative 1 plus 3 over x. And that's going to equal 2. So we're going to end up with negative 1 minus 3 over x is equal to 2. Add 1 to both sides, and negative 3 over x is equal to 3. What I'll do here is I'll multiply by 1 over 3. And what that'll do, and by the reciprocal, because that works, is that'll give me negative x is equal to 1. So I can move that over. X is equal to negative 1. These are our proposed solutions. Now I'm going to check them. Okay? If they exist, we're all good. And I'm not going to plug them into the originals because these come from approximations. So first of all, I'm going to just plug it in here, all right? So we're looking at first case, 3 plus 3 should be equal to 2, 3, right? Absolute value of 3 plus 3 is absolute value of 6. 2 times absolute value of 3 is absolute value of 6. Bam, it works. What about this one? So here we got absolute value of -1 plus 3 should equal the 2 times the absolute value of -1. Whoa. -1 plus 3 is equal to positive 2 equals 2. The absolute value of -1 is just positive 1. Absolute value of 2 is equal to 2. 2 is equal to 2. That works. So both of these solutions work. So now we know what we're working around. And these are going to be some of our points that we're going to compare with. Okay, so now the final step is to compare these functions. I have to keep checking if the microphone is working because it turned off in the middle of when I was almost done with this, and I didn't notice when it turned off, so I had to restart again. And right here, I have all of the points of intersection or solutions or any of that. And I'll go ahead and categorize them here. We always have to keep negative infinity. What? This marker's struggling. I'm going to switch markers. I'll switch to this marker. It'll probably look similar enough. This is normal marker suffering. There we go. Okay. I'll use this to fix that. Okay. We always have to keep these two in mind no matter what we're doing. Okay? And just keep in mind, these are the same color from now on. Oops. I just got that on my nose. Our -1 and 3 were our solution, our intersection points. -3 is the solution to x plus 3, or the root. We'll call it the root where it's equal to 0. And 0 is the 0 of absolute value of x. I'm calling it all the different things that it's called because the zeros, solutions, roots, it's all the same thing. Keep having to check my microphone. Now, here, I'm going to just categorize this with the line on top because it doesn't really matter what they mean. Now I'm going to look between each different set and figure out what's going on. Because one of these three things will be true. In fact, only these two things will be true between sets, because the only times they're going to be equal to each other are at our solutions, -1 and 3. It's pretty easy, right? So from here, what I want to do is go from, let's see. I'll just start from this side and go this way. -infinity to -3. And the way we do these is we just want to find something in between, because I have it already set up right here on my graphing calculator. You'll notice how within each of these ranges, it's always going to be one's greater than another. And I have it set up specifically so it'll work out that way. That's why I chose these, because we have our -infinity and positive infinities, our solutions, and our zeros. Those three things are going to create those turning points that we'll need. Okay, from -infinity to -3, what's something that exists there? -4. So what I'm going to do is I'm just going to start writing stuff out. -4 plus 3 with the absolute value. What I'm going to do is I'm going to flip this to 3 minus 4, because that works. Oops, there we go. I'm getting these markers to work. And what that's going to be equal to is absolute value of -1 is equal to 1. Okay, let's look at this one. 2 times the absolute value of -4 is equal to 2 times 4, because we make this positive. Whenever we have the negative in the absolute value, remember we make it positive. 2 times 4 is 8. So g of x is greater than f of x in this case. F of x is less than g of x. And that was from, that's not the right side, -infinity to -3. Okay, I'm just going to keep checking all of these. At this point, this might be enough for most of you, so that's probably fine. But I'm going to just keep going through this just for some extra practice. If you want to actually go through this on your own and just see what you can find, that also is not a bad idea. Right here, I'm going to look from -3 to -1. So I'm going to plug in a -2. And for this one, I'm actually just going to, I'll write it out. -2 plus 3 is equal to 3 minus 2 is equal to 1, because absolute value of 1 is 1. Now, same thing here. 2, negative 2 is equal to 2 times 2. That's wrong. Something's not right. No, it's not. Nope, it's positive 2. It is equal to 4. And if you look at this, yep, all that's good. G of x is greater than f of x here also, so we're looking at negative infinity to negative 1. Let's check on the graphing calculator. And yep, in that range, it's still true. So I was able to just change this because both of those exist in that range. Okay, now we're going to look at the next one. Negative 1 to 0. Easiest thing to do here is negative 1/2 or negative 0.5. So we're just going to go there. Negative 0.5 plus 3. Again, we're going to flip it. 3 minus 0.5 is equal to 2.5. Right? Get rid of absolute value because it's already positive. 2. And in this case, I'm going to do negative 1/2 because you'll be able to see it better. Is equal to 2 times 1/2 is equal to 1. Which one's greater? This time f of x is greater. So it's going to go in here, and that was negative 1 to 0. So we have our first one in our negative 1 to 0 area. And I'm just going to keep going. You have no idea how many times I've had to restart this because I've made small mistakes and couldn't take it back. From 0 to 3, 1 is a solution, or 1 is inside. So I'm going to just do 1 because 1's a really nice number. And I'm not even going to write it down this time because there's no subtraction, so it's quite easy. 1 plus 3 is 4. 2 times 1 is 2. 4 is greater than 2. So what we're going to have is I'm going to expand this 0 to 3. And once again, we can check here. And if you look at it, we're going from negative 1, right? Negative 1 all the way to 3. And f of x is greater than g of x. So we're still looking good here. And our last one right here, from 3 to infinity, I'm just going to choose positive 4. What's 4 plus 3? 7. What's 2 times 4? 8. G of x, which is 8, is greater than f of x, which is 7. So that's going to go on here, which means this is our final solution. So from that really big, scary problem where we had this, if I remember correctly, it was square root of x squared plus 6x plus 9 is equal to square root of 4x squared minus 3. We went from this, and we were able to compare all of these. Now, these are approximations, but they're surprisingly accurate, especially for bigger ones. It's going to work really nicely if you do these approximations. And also, that trick I showed you in the beginning with the hyperbola, that's what made all of this possible. So that's something I definitely recommend trying. But for now, that was the end of this video. Thanks for watching, and I'll see you next time. This was Deep Thoughts with Deacon.